Okay, so this is the second video of mental representation. Now we're going to get to talk about the physical symbol systems hypothesis. So before we get that, I want to talk about something called a mental architecture. Mental architecture is a model of how the mind is organized and how it works to process information. Essentially, we need to figure out how it could be the case that the mind is putting everything together and providing a cohesive experience so that you could imagine rotating a number 5. And how is it even doing that? How do all of the parts work together? What format is it using? How is it? What information is it processing, and how is it doing that? How is it transforming it? How is it organized, basically? We need to develop a mental architecture, we think, if we are to develop a full account or a general account of how the mind represents, which it seems like it does. So ideally, if we want to explain our experience, we need one of these. So I was talking about information processing models of cognition, because we are in the late 20th century using the information metaphor, thinking about the mind as processing information. To a certain extent, I think we're still in that world. This is the information age, of course. And there's going to be two very big mental architectures that we'll talk about: the language of thought hypothesis and connectionist models, but there are others. The reading goes into it in some detail. And we will, in this class, eventually cover everything, or at least all of the major models of mental architectures. So we're going to first start off with diagrammatic symbol structures to help present this idea of the physical symbol systems hypothesis. And then we're going to do the language of thought and then wrap up. So the physical symbol systems hypothesis was presented by, or proposed by Alan Newell and Herbert Simon, who argued that there was going to be some laws of qualitative structure governing cognitive science. And they made this claim that physical symbol systems were all that intelligence was. Anything that is intelligent is a physical symbol system, and any physical symbol system is capable of intelligent action. So it's a pretty strong claim. And I'll try to describe what they're saying. So symbols are physical patterns. Words are symbols. Images can be symbols. Just any sort of physical entity of some sort. They're patterns that can be manipulated, or can be perceived, or can be interpreted and understood. They can be combined to form complex symbol structures, right? So they are in the world in some way, and they can be modified. A physical symbol system is one that can manipulate these complex symbol structures. So a physical symbol system is the kind of system that manipulates words, or can manipulate images, or can just manipulate all sorts of things. And so when the system does that, when it manipulates them in a certain way, that just simply is representation. And that is just what we mean by intelligence. Okay. So in this view, computers, because they are manipulating symbols, zeros and ones, They just are intelligent. They just are, by definition. Now we can argue about that, but this is a technical term here for them anyway. Maybe they've co-opted a term that we want to say for other purposes, and so that's an argument we could have. But okay. So what we mean by intelligent thinking is the ability to solve problems. Intelligence here is the ability to work out which of those options best matches our values and limits. So it's not the best option, it's not the best answer every single time, but it is pretty good given the constraints. That's just what we mean by intelligence. And they argue that anything that could be intelligent must in some way, shape, or form somehow manipulate symbols in a systematic way. All right. So again, if all intelligence is problem solving, it kind of depends on what problems you're facing. This is going to open the ground for strong general artificial intelligence. They are AI pioneers, so of course they have no problem with that. In the next lecture, we'll talk about AI and whether we should think about that as intelligence. So we'll deal with that when we get to it. Okay. So in artificial intelligence, when you want to specify a problem, you essentially need to specify the problem space. You need to figure out what kind of solutions are possible, what your goal is, and how to manipulate it, how to manipulate the current environment to get to that goal, which means you must be able to represent the current environment. You must be able to represent your goal environment. You must be able to represent represent how you could change the current environment to the goal. And you must determine if the current environment has changed to be the point where it is now the new goal. Okay? So that's how computers work. Maybe that's how we work too. Maybe, perhaps. The problem is that for anything more complex than really like throwing dice, problem spaces are generally too large to be searched by brute force. You've got to come up with some shortcuts. So think about playing poker. Even shuffling a deck of cards, right? You've shuffled decks of cards before. I can guarantee you with 99.99% certainty that every time you shuffle a deck of cards, let's say you shuffle it a couple of times, no human ever has or ever will shuffle a deck of cards in precisely that proportion or that combination. And that sounds crazy, but like you do the math, 52 factorial is a number greater than, it's probably somewhere on the order of the number of grains of sand in the universe. So since we can't be exhaustive, we must come up with some quick and dirty rules. So for example, you must be able to like eliminate the really, really shitty options. Don't put your queen out so early that it's going to get taken. That's a good heuristic in chess, for example. So the physical symbol systems hypothesis is a way of manipulating symbols without using brute force, but getting to a solution in some way. So you represent the world somehow, or at least you represent symbols, and then you manipulate them until you get them to be different symbols. And those are your goal symbols, ideally. So Importantly, physical symbol systems are not themselves intelligent, because then you'd have to explain what that kind of intelligence means. So a computer behaves intelligently, and it just is what we mean, but the algorithmic process is not itself intelligent. It's importantly, it has to be algorithmic, right? So no parts of it can be themselves intelligent, because then they would have to be made of other physical symbol systems, and it's just an endless regress. So let me give you an example of a visual version of this. This is a program called Whisper, and it is a computer program that purports to represent some physical objects that are unstable blocks, and it is to manipulate it in a stepwise process until the computer deems that it is stable in some way. So we go from the initial state, and then the little wedge at the top starts falling, and then it hits the other step or the other object. The D object and the B object end up hitting the bottom nines, and so the system deems that at this point it is now a stable solution. This is a stable object. All right. Well, based on its weird rules that I didn't go into very much detail to explain, sure. Perhaps a more convincing version of this would be a Roomba, or its predecessor, a Shaky. It's a robot that could interpret its environment and solve problems. So it can move around in a room around and not like hit objects, right? It could move around objects even if they kept switching the objects around them. Roombas do this all the time. It doesn't seem that surprising to you, but they must have a way of representing the world and manipulating it in a stepwise algorithmic fashion in order to get to their goal, cleaning up every bit of flooring. Okay, so the physical symbol systems hypothesis, you can imagine representing it diagrammatically by certain goals. You can make computer programs, design robots that do this. Cool. All right, that's fine. That works for AI. Simon and Newell were super into AI, so maybe that's all they care about. But how do we think about humans? How do we think about our intelligence? How are we to understand how we organize thoughts, how we think about representing the world? And that takes us to the language of thought hypothesis. So there's going to be three assumptions to start off with here. First, materialism. The mind in some way is caused by the brain. So you have beliefs and even perceptions, even parts of your brain activities. It just is. There's just no souls, there's no spirits, there's no spooky mind things. Mind in some way is dependent on the brain. Mental representation, which was the earlier video. It seems like we represent the world. We have a thisness. We are talking about the world, thinking about the world in some way. And finally, when we think about the world, we can act. The idea of getting a soda, the example from the literature is actually a beer. I should have just said a beer. The idea of getting a beer is somehow able to cause you to get up and go get that beer. Okay. All right, so those are assumptions, and now let's talk about motivations. First motivation is the mental causation, but applied to contents. I get a drink. My mental representation has some contents, which I'll describe in a little bit. And then I use that to go get it. Cool. The idea of a beer mattered in my head, and it was relevant to me getting up and moving. Cognitive scientists were also fascinated by language. So how in the world could we learn language? And so there's this argument called the poverty of the stimulus argument, which is if we're only ever exposed to positive instances of language, there's literally an infinite number of ways that language works, or sorry, that language could work. There is an infinite number of ways you can imagine arranging not just sounds, but motions and intonations and positions. When you say the color red to a baby, is it the intonation that matters? Is it the sounds? Is it where you are in the room? Is it who you are? Is it the angle at which you're speaking? Like there's an infinite amount of information, and the baby somehow has to figure out which of the many possible things you could be referencing, and they do eventually. They learn relatively quickly how to manipulate an entire language. Finally, it seems like our thoughts aren't just random. We make reasonable inferences a good portion of the time. So the distinction I mentioned earlier is this distinction between content and so the content of a belief and its vehicle. The content is what you believe the world to be. So the beer in the desire to go get a beer, okay? That is the contents, that is what you represent. You represent contents, you don't represent the neurons that are used to think of the beer. That's not what is in your mind, right? So it's in your brain somehow. Some neurons are firing, or if you're a super smart AI, some zeros are turning into ones somehow. But the content is different than how it's doing that. In linguistics, you might call that distinction syntax and semantics, right? The meaning of the sentence versus the spoken sounds. And again, all representations, you can make this distinction between content and vehicle. So there's beliefs, desires, propositional attitudes, sure. There's also probably some brain states. All right, so vocabulary catch up. Lots of different disciplines have come up with the same distinction again and again. So it's kind of frustrating that we have to like reintroduce it each time. Here we're talking about content and vehicles. If you were learning this in a linguistics class, we'd be talking about semantics and syntax, right? Semantics being about meaning, the syntax is the form of the sentence, the grammar. We might be talking about intention and extension if this were a philosophy of mind class. We might be talking about meaning and form. Algorithms and representations are a little bit ambiguous, but you know, we want to distinguish the about what something's about with how it gets to you. So, okay, the content of your belief represents in some way an object in the world. Mental representations, of course, we already talked about this earlier. They have content that can be true or false. Mental representations have content. That's certainly true. And we call them true if we think that they accurately represent reality or something like that. The stop sign was red, yes, that you had the right contents. all dogs are mammals, yes, that kind of stuff. All right, so how the hell does content do a damn thing? It doesn't seem like there's content involved in your neurons. They're just firing. It doesn't seem like it's involved in any brain states. They're just doing stuff. At some point, your mind comes into the picture and it starts doing things. So imagine an opera singer sings at a very high pitch and causes a glass to shatter, and she happens to be singing the word shatter. Was the word the thing that made the glass shatter, or was it the sound coming from her voice, from her lungs? Well, that's tricky because it seems like causation happens at the level of physical objects. Like the word shatter didn't cause the glass to shatter. Content properties are not physical properties. So if causation, if things can only be caused, if you can only have causal explanations by the formal structures, how the hell does meaning ever get a foothold? So it would be worrying if your thought of the beer actually had nothing to do with you getting up and getting the beer. The solution, according to some people, Jerry Fodor among them, is what's called the language of thought hypothesis. The language of thought hypothesis is a hypothesis about vehicles of mental representations, and basically it's that vehicles have a certain structure somehow. Your mind that is isomorphic, that is has the is geometrically or is structurally similar to the contents of those vehicles. So remember when we were talking about the mental representations in the earlier video, and we talked about the various different approaches. This is one approach, right? Like there's just a resemblance relationship between the vehicle and the contents. Now, all of the three approaches that I gave you for mental representation had problems, and we'll see the problems with language of thought soon, but it's going to be the same problem as the representational view. So the structure at the level of the vehicle explains how the content might cause anything. Your beer thought is related to, has a resemblance relation in some way to your brain states. The brain states are the ones that cause you to do stuff. But the resemblance relationship is pretty strong. All right. Causation through content is determined by the causal structure interactions between physical structures. It's the vehicles that do everything. It's your brain states, not your mental states, that cause the actions. And furthermore, these physical states, they have a structure that is, the term is compositional. We talked about like how images could not be composed, but thoughts could. Representations can be composed. You can have the idea of a blue mountain, blue plus mountain, blue mountain. And so these physical structures have that kind of structure, which means that they can be added together in a algorithmic type way. And that means that the causal relation, or at least the relationship between these quote sentence-like items in your language of thought. And again, this is your universal grammar. This is not a language in the traditional sense. This is just how your mind is organized. It's the architecture of your mind is the language of thoughts. And so your mind is organized in a particular way that directly relates in a resemblance way to the contents that you learn in your language. Okay? This is one of those views that I have to explain very slowly because some people find it very confusing. And you can literally dedicate an entire career to this. So we won't spend much more time on that. So one of the arguments in favor of this is that if there is an information processing, so if information processing is a form of computation, we need something to get content off the ground. Otherwise, the computer will never learn anything. There's no there. So if we were right about the information metaphor, then the way our minds are organized must be something like a structural resemblance between our mental organization and the world that we perceive. And so when we learn a language, what we're doing is just hypothesis testing to match up the language to how our minds are organized, how our internal thoughts are organized. We make up these rules, we make up these hypotheses and test these rules by trying to use language. We try to use the intonation or the position, and then eventually we use the word red, and people are like, oh, they're saying red. Okay, and we're like, okay, so it's the sound that matters. It's the particular thing, not who says it where or how. One of the weird things about language of thought is that means that your initial, if we can learn any language and the information processing view of mental architecture is true, a view of the mind is true, then your hardware, so to speak, your mental hardware must be at least as strong as any language, at least as expressively powerful as any language ever learned by any human. Think about it like a computer. If you can play all of the games, your computer must at least have been powerful enough to be able to play all of the games. So if many people have the exact same model of computer as you do, and they install different games or different applications, then that means that your computer could have also played those games. In the next lecture, we're going to talk about what that means.